to get money. Okay, so yeah, so basically last week we went over a lot of things. If I remember, I know we started from tries, the trie data structure. That is this, right? And then wait, am I recording? Okay, kind of. We started from the trie data structure, right? And we went about what the trie data structure is, and then we looked at a few applications like it can be used to design a type ahead system, even things related to like dictionaries and other stuff, right? Like the thesaurus thing, they all use kind of like the trie data structure, right? And we said usually when you have like many words and you want to like create a dictionary, not a dictionary as in like Python dictionary or something, but like the normal dictionary, like Oxford dictionary and everything, like a collection of words, usually the trie data structure. So if I want to put, these words inside, some data structure where I can easily search, find and, check all those things, I can just use the trie data structure. So it has, a node, right? So this is a whole data structure and each point here is actually a node, right? So this is our root node. And I want to insert the word, let's say AMN, right? I first start at the root node. Then I check, does it have a child whose key is A? If it's not, I just create a node for node A. Then I go down, recursively, down A's path. Then I'm like, hey, A, do you have a child M? If it has an M, good. If it doesn't have, I create the node M. Then I'm like, okay, the last, character is N. Then I'd be like, M, do you have a child N? If yes, I just, continue. If not, I create the node N. Then I go on and so on and so forth. So we also said it's called a prefix tree, right? Because it can be used to find prefixes. So for instance, if I want to find, all words in my dictionary that begins with, let's say, the letter A, right? From the roots, I can just come to A, right? If I come to A here, I know, every single person, beneath A, actually, every, word here is actually, the word that has its prefix as A, right? So it's actually called a prefix tree. Then we went over, the insertion and find, and we said the algorithm was actually a very simple algorithm. And if you went through the problems we give for the week, you'd actually see like, some 2 questions or so that basically teach you how to implement. It's a very simple implementation, right? That this is a definition for the class node, for the node itself. Every node has children, that is a dictionary, and a property, an attribute called is end, and its end is true if it is the end of a word. So for instance, if I ask you, is AE a word in my trie? The answer is no, because if I come here A and I come here E, right? E is not circled with red, right? We circled with red if it was the end of a word, right? And because E is not the end of a word, I can just tell you, it's not. So that's what the is end field does, right? If you get to the end of a word, you just set the is end property to true, right? Then, went over a few things. This was the insertion algorithm, very simple algorithm. If not watch the recording, please do to watch last week's recording. We can't use this week to go everything. Then we came back to the main data structure for last week. That was the graph data structure. In case you weren't here last week, this is still a time to, do some recap. We said the graph data structure is basically used to show relationships, right? So the relationship between this node, and this is also a node. And a tree is actually a graph. We said even linked lists can be graphs. But the thing with a tree is, a tree has to be connected, right? All the nodes of a tree has to be connected. That is one thing. So say a tree has to be fully connected, and there has to be no cycles, right? So a tree cannot have cycles. So there's only, from the roots node, there's only one path to that particular node. So if I take this node here, the only way to get to this node here, from the roots node is come down, then come down. That is the only way to get to this, right? There's no other path. So a tree is a graph, but it is fully connected and it's acyclic, right? No cycles. But if I take, but graph is a more general thing, right? It can be disconnected, right? So this whole thing is a graph. There's one node here, there's one component. We call them components. The coming weeks we talk about a certain algorithm to find the number of components in a graph. And we said the algorithm is called union find. It's a very beautiful algorithm, trust me. It's also used by Kruskal's algorithm. That's something we talk about later, or even today. So this is one component. This is also another component. This is a graph, right? And yeah, so then we went over some properties of a graph. So we said graphs actually have vertices or nodes. So this is a vertex, right? These circular things, they're also called nodes. And what it joins them, this line is what we call the edge, right? So we have the vertices, then with the vertices, then we have the edges. Then we talked about the fact that we may have, the graph may be acyclic, or what do you call it? Maybe directed or undirected, right? So we said this is an undirected graph, right? And the relationship goes in both directions. So we use the example of Facebook friends or LinkedIn connections, right? Where we are like, if you're my connection, I'm also your connection, right? The relationship goes both ways. Then we also discuss directed relationship, where let's say teacher student, right? So this may be the student, right? So you're a student, to this teacher, right? That relationship goes in one direction, and it's good to know both of them. So we have the undirected, like we have here, then we have the directed, like we have here, like so. Then one other thing that we talked about how to traverse a graph, right? But before we did that, we went through graph relationships. sorry, graph representation. Then we said we can actually represent a graph using an adjacency list, right? So where, if we have, so we said, like, let's say you have, you have one thing like this, and it starts a relationship to, let's say, 3 other things. So let's say this is A, this is B, this is C, this is D. One way to represent it is to use, an adjacency list where the key is the node, right? And the values are the other things that the relationship to. So here, this would be A, this would be, then we have B, C, and D here, right? Adjacency list. And we said this list version can actually be implemented with a linked list, right? Just like this, right? Can just be presented with a linked list. Then we said the other representation is what we call the matrix, right? The adjacency matrix. So here, the relationship we have is that let's say there are 3 nodes or 3 persons, right? 1, 2, 3, 4, 1, 2, 3, 4. If one has a relationship with 2, we can just put 1 here, right? If one, I think we use an example, right? We use this example, I think, right? So 1 has a relationship to 2. So 1 and 2, right? We have this one here. 1 has a relationship with 4. So 1 to 4, we have it here, right? What else? And then, but if you look at this, actually a directed one, right? This actually a directed one. But let's actually populate this table again as a recap for others to also see. As I said, I'm actually a stronger fan for adjacency matrix, and I showed you why. It's very easy to implement. Just use a dictionary and you're off, right? So if you want to like do this right now, let's change the colors. So we are like 1, 1 has a relationship to 2, right? But it's an undirected edge, right? It goes both ways. So 1 to 2, they have a relationship, right? That means that 2 to 1 also has a relationship, right? Then 1 to 4, that is this guy, right? Like this 1 to 4. Also, so 1 to 4, and it's undirected, right? So that means 4 to 1 also is valid, right? 4 to 1, right? Then we do the same thing, 3 to 4. So 3 to 4, it's valid. That means 4 to 3 is also valid, right? And so on and so forth. 2 to 3, then 3 to 2, right? 3 to 2, then all the other ones get zeros, right? So if there's 1, that means it's a relationship between the 2 entities, else there's not, right? So that's adjacency matrix representation. And we said it's very easy to, create this. Then we went on to, how, in coding problems, I usually get a graph. So you don't get a graph looking like this, right? You don't get a graph like this. You don't even get a graph like this, right? And you hardly even get a graph like this, right? Instead, you get something like this, right? Get something like this. But it is up to you to, create the graph out of it. Went through the very easy way to create a graph given an input like this, right? Using the call schedule problem. So if you've not watched last week's recording, please do all to go through that recording and watch it. It's super helpful. Then we discussed something called the degree of a node, right? So I don't know if people want us to go through the call schedule problem again. I think we should, because we're talking about something called topological sorting. So let's start from here, right? And this, so basically also went over this, general algorithm for many graph problems, right? I just need to understand this algorithm, and many graph problems will be very simple for you, right? So let's go over the call schedule problem. Today we're doing call schedule 2. So last week we discussed the fact that is it possible to complete these calls, like this calls? So you'll be asking a question about what is the order of completion, right? How will the courses be completed? In what order are they going to be completed, right? So let's just take this like this and move it somewhere here. And let's go over, even if you weren't here last week, just follow us and everything's going to make sense to you. Oh, and lastly, we also discussed, oops, I almost forgot. We also discussed traversals, right? How to traverse a graph here. Then we started with a tree traversal as a premise, right? As a premise. So we are like, you can do a DFS, right? Where you go down, 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 right? I think we use this diagram here. Like DFS, you go down, 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 down. And we have the BFS, where BFS, this node, you consider its neighbors first, right? BFS is more like a family man. Consider its neighbors first, right? Then consider its neighbors first, right? Okay, good. Now let's now we start today's session, and we'll first start with the course schedule problem we did last week. But today we're going to focus more on how are the courses going to be completed, right? So course schedule 1 that we did last week was, is it possible, right? Is it possible to complete the courses, right? I'll explain this very soon. To complete the courses, right? So this is what the problem was. So the problem is we have please, even if you didn't come last week, just follow me, really get everything we're saying here. I think the green, the yellow is not that deep. Okay, I think the green is better. Okay, so the question we're solving last week was, assuming you have a couple of courses, right? Like you're in a certain school, then there's a course like CS 1110, there's CS 2110, right? And then let's say there's CS, 3410, right? And you want to take this course, right? You want to take CS 3410. But then the school tells you that to take CS 3410, you should first take CS 2110, right? So CS 2110 is a prerequisite. Then take CS 2110. They tell you should take CS 1110 first, right? So that's basically what the course schedule problem is. That I want to take a certain course, right? But some courses have prerequisites, right? So is it possible for me to take, all these courses, right? That's basically what the problem is telling you. So looking at the diagram we have here, is that to take course 2, right, you should first take course 1. To take course 4, to take course 1, you should take course 4, right? To take course 1, you should take course 6, take course 5, you should take course 2. That means that a certain course can have more than one prerequisite, right? One prerequisite. So we said the input to such a problem may be something like this. So you have a list, right? Then, it's a list of lists. Then the first one is the course. So let's say this is 2, right? Course 2, it has prerequisites of 1. Then, we go on to the second one, that is this part, right? Then course 1, that's a prerequisite of 4. Then course 1 again, that's a prerequisite of 6. Course 5, it has a prerequisite of 2. Course 7, and that has a prerequisite of 6, right? Then they're asking you, is it possible to take all the courses? So is it possible to take course 1, 2, 3, 4, 5, or whatsoever, and so forth, right? Then the first question we ask ourselves is, when is it not possible, right, to complete all these courses? And can someone remind us, when is it not possible to complete all these courses? When is it not possible? When is it not possible to complete all these courses? When is it not possible? Anyone, when is it not possible to complete all these courses? Let me check the chat. Good, when there's a cycle, exactly, right? So assume something like this. I'm like, to complete course 1, you have to complete course 2, right? To complete course 2, you have to complete course 3. And then I'm like, to complete course 3, you have to complete course 1, right? This is not possible, right? So I'm like, okay, I want to take this one. They're like, take this first. I want to take this one, like, take this first. I want to take this one, they're like, take this first, right? That means it's never possible, right? So this question is just asking you, is there a cycle in our graph, right? So you learn graph cycles, but then they give you a real world application of it, right? That is like course schedule, right? And that is, the essence of what we are learning, right? So the whole thing is they want to check, they are asking you to check if there's a cycle in this graph. But the thing is, this is the inputs they gave you, right? They didn't give you the question in this format. If I draw this, it's very clear, right? But it's not possible if it's a cycle. So we said you take this input, then you create your graph out of it, right? You create something like this out of it, right? So let's do that very quickly. They're going to take this graph, right? So this thing is like the same thing written here. So I'm just using this. I think this is cleaner to see. So we are like, okay, so for each course number, we're going to draw a node for it, right? So this is course 2. If you take course 2, you have to take course 1. Then to take course 1, you have to take course 4. To take course 1 again, you have to take course, let's bring that one down here. You have to take course 6, right? Then to take course 5, you have to take course 2, right? Then take course 7, you have to take course 6, right? So this becomes our graph, right? This is our graph. And so let's check if there's a cycle. I don't think there's a cycle, right? Like there's no cycle, right? There's no cycle. That means it's possible to take all the courses, right? Like it's very possible. But then you can't just do this and be like, hey, interviewer, if I read the graph, this is what I have, and there's no cycle, right? You can do that. So now you have to write code. So when you get question like this, you have to now represent the graph in code, right? And we learned about 2 ways to represent graphs. You can either use the adjacency matrix, right? We have here, or the adjacency matrix. So let's go with this. As I say, it's very easy to construct, especially in programming languages like Python and Java and so on. So to construct this, what we do is that we're going to construct, a dictionary like this. So let's say this is a dictionary. And we're going to have, the key to be the course, right? Then we're going to have the value to be the prerequisites, right? So there's the prereq, right? And this, the course, the main course, right? So with this, we can just start populating our table. So we're like, you know how to put things in dictionary. So you just loop through this, right? Then, for every course, a course can have more than one prerequisite. We use a list for the values, right? Adjacency list. So we can put 1 here. So 2, 1, then 1, has 4. Then 1 again has 6, right? Then 5 has 2, then 7 has 6, right? So this is basically, the graph representation of this problem, right? We just construct this with our graph. So the graph, so we create a graph variable, that's a dictionary, and then we populate it this way. The next thing we do is that we create a function, right? So let's say we call the function complete course, right? Complete course. Then it's going to take a course. So as we've been, we discussed recursion about a month ago, and every day we are like, assume the function works. We're going to do that same assumption here, right? So complete course is simply a function, right? Let's write this specification here. So complete course is a function that it returns true it returns, this is a specification of the function. It returns true if, we can complete, this course, right? So this is the specification of our function, right? So now we're assuming the function works. We're assuming that we can complete this course. We're going to see that same trick, right, to do it, right? So it's a function that returns true that we can complete the else false, right? That's just implied, right? Else false. So the question ask yourself is, when can I complete a course, right? You can only complete a course if you can complete its prerequisites. Does that make sense? If I can complete a course prerequisites, that means I can easily complete that course, right? Does everyone agree with that? Does everyone agree? That it's only possible to complete if you can complete its prerequisites. That is if it has in, right? If it has like no prerequisites, then we're done, right? So now let's assume it has no prerequisites first. So if, right, how can we know a course has no prerequisites, right? For now, let's assume we have some course here, course 3, and then that is empty, right? So we can simply say that if, if inside our graph, right, we check the prerequisites of that course, right, and it's empty, I can simply return true, right? You can also say if not graph, of course, that also works in Python. We're not just doing Python, so let's just write this. We can return true, right? So if the course has no prerequisites, I can definitely complete that course, right? I'm done, right? Now let's assume it has prerequisites, right? If it has prerequisites, let's write the base case. Let me change the color for the base case. That's going to be an interesting thing. All right, let's just go here. So let's go to a recursive. So this is our base case, right? Base case, right? Base case. Now let's go to our recursive case. Our recursive case is now to complete a course, I have to first complete its prerequisites, right? So I'll go through for every prereq, right? Let's just call it prerequisites. In how do I get the prerequisites of the course? That's when the graph representation comes in handy. So I'll be like graph, graph square brackets the course. So I'm going to get every prerequisite of this one. Wait, I want to change this guy. Bro. Sorry, I'm just a bit color something. This recursive. I just want the thing to stand out. Wait, let me change this to also base. Okay. All right, let's continue. So now we're going to assume the function works, right? Let's assume the function works. So for every prerequisite in the prerequisites of the current course, we check if we can complete it. Now assume the function works, right? So if I assume the function works, that means that if I can indeed complete the prerequisites, the function is going to return true to me, right? If I can't complete that prerequisite, the prerequisite is also a course. Don't forget, each prerequisite is also a course on its own, right? You can simply write if, right? If not complete course, of the prerequisite, right, I can simply return false. So this is what we're doing here. We're assuming that our function works, right? So I'm like, hey, go through all the prerequisites of the current course, right? And for each of these prerequisites, check if we can complete that, right? Because I'm assuming my function works, I can simply do this, right? So then I'm like, if this function call returns and I was not able to complete the prerequisites, then I should return false, right? Because if I can't complete a prerequisite, then I can't even complete you, return false, right? But then if this for loop completes successfully, right, without this return false ever executing, right, can then come outside and then I'll be like return true, right? So that's what's happening here. So you take the course, right? You take the course, you're like, hey, do you have any prerequisites? If you have none, I can return true, right? Then a recursive case, go through every prerequisite you have. If you're not able to complete the prerequisite, return false. But if this for loop ends successfully, right, then you can, at the end of the for loop, outside it, you can then return true, right? Does that make sense to everyone? Does this code here make sense? Does this make sense? And this is the format of graph questions. Most of them you come across, this is basically the format, right? Now let's add one last thing. The other thing we can add, right, that somebody's like, okay, then when am I going to return false? So now if you look here, right, this is the base case. The base case is only returning true, right, out here. And this is also returning true out here, right? Like there's no return false, inside our graph, right? Like you don't think of this recursive case, don't think of even the recursive case, right? Like don't think of this guy. Think here, this guy is returning true, right? This guy is also returning true here, right? But the thing is, when am I going to return false? When is it not possible to complete it? Is the question we're asking right now. That is when the concept of a cycle comes in. Now, generally in graph questions, we check a cycle, right? Let's see how cycles happen. So cycle is going to happen this way. So assume you have, we start at course, let's say course 5, right? And for course 5, we have a certain thing, a certain list that is tracking a path. Usually it's a set, right? So let's say we have this set. Let's use this. That is, tracking our path. So we are like, okay, now we want to complete course 5. So we add 5 to our set, right? Then we make the recursive call, right? As you can see here, we go to the prerequisites of 5, right? We go through the prerequisites of 5. You're like, okay, so that is 2. So we come to 2 here. So we add 2 to our set, right? 2 is the one we want to process next. But before we add 2 to our sets, let's do something. Okay. So before we add 2 to our sets, wait, there's something in the chat. Let me check. Okay, sets make sense. Okay, good. So let's start again. So 5, right? We want to complete course 5. We put 5 in here, right? Then we go to course 2. Like, okay, 2, we want to complete here, right? So we go to complete course 2, right? Then for course 2 also, we have to go through 2's prerequisites, right? Now, assuming that we see 5 as one of 2's prerequisites, we can be like, oops, that's not possible. That is a cycle, right? So this is what we mean. We add 5 to our sets. Then we come to complete course 2. Then for course 2 prerequisites, we see 5 again, right? We see 5 again. We're like, hey, 5, we already saw you. You're the ones we're currently processing. You're in the path, right? In the path, we are currently, trying to complete. This is the second time we are seeing you. That means there's a cycle, then we can return false. So in code, what we usually do is that we pass an extra argument to, to the function, right? So we pass an extra, we usually call it vested or seen, right? Let's use seen, right? Seen or vested. This is vested. I think vested is cool. V is nice. Maybe nicer than S, I don't know. So then we do this, right? Then we check, right? Inside our base case, then again, we check if we should actually even check it. And let me delete this for now because we know what the function is doing. Then we can do here, if course in seen, that means that you are currently trying to complete. So sorry, why am I messing this up? Is it invested, right? We can return false, right? So but what that is telling you that vested completes the course that are on the path, right? The path you're trying to complete. So here you had vested, right? Then you are going through one, and as part of one's prerequisites, you see, let's say 5 again, right? You can simply check if, hey, I've seen 5 before, right? 5 is in seen. That is the path I'm trying to, complete. And I've seen it again. That means it's not possible to complete. So there's a cycle. And that's how you check a cycle, right? If cost invested. So if cost is not invested and cost is not a base case, here you add, the current cost to vested. And this way you populate vested. So vested.add, you put your cost here, right? So if you put the cost here and make any recursive call, right, on any of these prerequisites, and that prerequisite, ends up being the cost itself, we can then catch it here. Wait, does this make sense? Does this cycle check make sense? Does it make sense? How we populate, for every current cost, you add it to your path, that is a vested. Then if you go through any prerequisite and any recursive call, and you see that cost again, you can then return false, right? And then that false is going to be caught here, then you can return false. Does this make sense? It's left one line of code, then we are done. But does this make sense? Does this make sense? Does this make sense? How we are checking for the cycle? We add the courses to the path, and we've seen it before. Then the last thing you do, right? The last thing you do is, now we know that when this for loop ends, right? If this for loop ends successfully, that means you're able to complete the current course, right? That's something we all know now, right? Like if this for loop ends without ever, returning false inside the for loop, that means you're able to complete this course. And once you're done, again, you remove, from your vested the current course. That's like, hey, we are done with you. So vested.remove, the course, and then you are done. And this is, trust me, this is a pattern of many graph problems you come across. This is just the pattern, right? First of all, you have, your base case. This is your base case, right? Your base case. Then, you track whether there's a cycle. Then don't just want to check if there's a cycle, right? And now you just use a set, right? You pass a set through it. If what you've seen already is, is in your set, something you can use a dictionary also. We would look at other variations of graph problems. So you actually use a dictionary and it's very helpful, right? So let me show you an example. Actually, don't worry, just read that later. And then, you add the thing to your path, to your set. Then you go through the prerequisites. You check in here. If you're not able to complete the prerequisites, then you return false. But if you're able to complete that course, then you remove it from this and then you return true, right? And this is basically the format of mini graph problems. And trust me, when I learned this thing in 2021, it really saved me a lot. I have graphed with a lot of companies like DoorDash, like Mongo, and a couple of other companies. And I think this is like the main graph question I had solved. And I tried to understand it. And I just had to optimize this, apply this wherever I went, and I was good. Okay. Now, the next thing you want to consider is what is going to be the order in which these courses are going to be completed, right? So if you look at this thing, right, right now, right, the order of the course, can someone tell me the order in which these courses should be completed? The order. That's the next question we are solving. The order in which these courses are going to be completed. Anyone? What is going to be the order in which these courses are completed? There can be more than one order, right? But just tell me any. The order in which these courses are going to be completed. Anyone? The order in which the courses are going to be completed.
So 5, 2, 1, 6, 7, then 4.
Then 4. Okay. So
Or or you can complete 4 before you come to 6 and 7.
Okay, good. Yeah, anyone else? What do you think is going to be the order? Or do we all agree with this one or the swap, the suggested? Anyone else? Anyone else? So the trick to know here is, if you look at the code right now, right? Look at your base case, right? This is the simplest way to complete it, right? That is the course has no prerequisite. That is the simplest thing. So you remember last week I mentioned something that if the node, right, has no out degree, right? If it depends on nothing, right, it's always the easiest to do first, right? Because not something. If you try to do 5 would be like, please go and do 2. Try to do 2 will be like, please go and do 1. Try to do 1 will be like, please go and do 6, right? Then 6 like, I'm done, just do me, right? And then you're done. That means that 6 is going to be done first, or 4 is going to be done first. Can everyone see it? That those ones who have no dependencies are always going to be completed first. That brings us to our next topic, topographical sorting. So topographical sorting is just, like a form of like sorting thing. You can think of that, arranges things in order in which they're going to be done, right? Based on dependency. So if I take this one, the order is going to be, number 1, any of those nodes with no dependency, right? So either 4 can go first or 6 can go first, right? Because they depend on nothing. If you trigger your recursive call on 2 will be like, let me revert this. 2 will be like, nope, you can't complete me first. Go and complete 1 first. The 1 will be like, you can't also complete me first. Go and complete 4. Wait, does this make sense? Does this make sense? Does this make sense?
Yeah,
The topographical sorting algorithm we are discussing here. Yeah. So that is how the order is going to be, right? So here, so one order, right? One pattern, right? I know it's kind of a bit tricky, but if you look at it, that's actually how it works. And I'll show you how you can easily identify that in the code. So here we can complete 6 first. Now we complete 6, right? Now once 6 is done, look here carefully. If 6 is done, we can easily complete 7, right? Can we all see it here? When 6 is done, 7 now, 7 is like, hey, now you can satisfy me because my previous 6 is done, right? Then we can complete 7, right? So we are done with this branch. Then if 6 is done, right? You can't complete 1, right? Because 1 will still need 4 to be completed, right? That's why you're using the for loop, right? That's why you're using the for loop here. When you complete every prerequisite, for that course, right? So 1, you've completed 6, that is prerequisite, but you still need to complete 4 for it, right? Then we can complete 4. Now, once you're done with 4, 1 is like, okay, I can then be satisfied, right? Because its 2 prerequisites have all been completed, right? Then 1 can come through. And if you're done with 1, 2 is like, yeah, you can also complete me, right? Because my prerequisite is done. So then 2, and if you're done with 2, you can easily do 5. So this is going to be one order, right? There's one order of it, right? That order is you can also do 4 first and so on and so forth. So you complete those ones with the fewest dependencies first, right? Now let's come to our code. And that's course. So course schedule 1 is it possible to complete all the courses? Course schedule 2, I think, is also what is the order, right? And order is what we call topographical sort. So it's something like this. So like you have notes here, then it's something like this. Right? This is a topographical sort order, right? Like the order in which you complete something, right? So here, this whole thing we just is what we call the topographical sort, right? So here, let's look at how we can catch this thing, right? When we're going to complete the courses. Now I'm going to number some lines of code, and somebody should tell me, right, where we can throw in. So now we just want to, we want to accumulate this guy. We want to accumulate this guy here, right? So I want someone to show me where we should put, a certain line of code, right? To, so let's say that line of code is, so let's say we want to accumulate it into a variable called results, right? So I want where I should, do something like results. So let's assume it's a list dot append, the course. So this is a line of code. We want to see where we should put that line of code. I want to show you how like things just build on one another. Okay, so this is a line of code. Now let's see where we want to put it. Let's number the lines. Let's say this is line 1. Somebody will say we should put here. So let's put line 1, line 2, line 3, line 4. Definitely not the comments, please. Line 5. Actually, doesn't matter. Let's just do it. I should have used like a grid or something. 1, 2. You can be like before or after or anything you want, right? I don't know if my handwriting is clean enough. I used to write on the board when I was in JHS. Yeah. They made us spend years to polish our handwriting, and now we don't even write. Okay. So now, where should we put this line? Anyone? I hope everyone can see the full screen. Where do you think we can put this? Anyone? And this is the line we want. Anyone? You can put your head, anything.
After line 5.
Okay, after line 5, we have an option.
Line 5.
So after 5, anyone else? Anyone else? You can also put in the chat. You can also talk. Anyone? So after line 5, anyone else? Anyone else? Okay, there's something in the chat. Let me open. After 12, I also have after 12 here. Okay, after 12. Anyone else? Anyone else? Anyone else? Anyone else? I mean, there may be more than one place. So after 5, after 12, anyone? Anyone else? Oh, that's what we have. Okay, good. Yeah, so both are correct. I just took a look at this and both are actually correct. So why after line 5? I think there's just one course, right? Like all the courses have no prerequisites, right? Then before you return from here, definitely you want to put it here, right? You want to actually, be like, hey, I've completed this course, you can put it here, right? So it's actually basically any part you are returning through, right? Like if I put it here, right? If I put it here, so let's assume, course 3. If you call the function on course 3, right? Course 3 will not go here. Like course 3 will not come in, course 3 will not cross line 6, right? Course 3 will just, just end here, right? So you're like, okay, we can then put it here. So we can put that line here. So res.append course. So this is one place we can put it. That's correct. That's good. And yes, after line 12 too is the same thing, right? So when do we come to line 12? We come to line 12 if we have been able to, if we have completed all these prerequisites, that tells us then we can complete the course, right? Before we return through. We can also put it here. Res.append, the course. It can also, it's just to be like just before you return through and we are done. Like that is all. You're going to get the topographical sort order perfectly, right? That's just it. Even if you want, right, you can even omit this base case. Actually, don't omit it. I mean, you can actually omit this base case. It will still work. If you omit this base case, there's going to be no prerequisites in the course. So this for loop is going to not be executed. Then it's going to come here, right? It's going to come here. Then, it will just work through. But just add the base case is very helpful. Prevents, wastage. Okay. And once at the end, when you print results, so what we do is that, I think I've explained non-local, right? Non-local variable. If not, look in the code channel. I think I was having a discussion with Richard in there on one day on it. You can see there. So non-local result, that simply means access this variable, across all the recursive calls. That is what it's going to help you with. And then, each time you complete it, just append. And when you print results at the end, results is just going to be, something pretty like this. And that is the topographical sort order. Very cool stuff, right? Does this make sense? Well, about going on to the next thing. I just want to see, so this basically, the pattern of graph problems, how you solve them. You write your base case, you write your recursive case, and please solve this question on LeetCode. Try to visualize it using the Python tutor. I wanted us to do something like that today. Like the tricks to understanding graph algorithm, because it's recursive, right? This is very recursive. You can actually use iteration though, definitely, but the recursive one I think really makes sense, right? It's very simple. Write this code, try to visualize it in the Python tutor, right? And try to see how the recursion unravels. It's so pretty. Now let's go to the next thing. Now, we are so used to, adjacency list and everything. Let's go to, where the inputs, right? It's a matrix, right? Let's look at an example where we can use this, right? We're now going to look at something like this, right? Where the inputs is something like this. But before that, does anyone have any question before we move to this? Does anyone have any question with this thing we just went through? Anyone? Any question before we go on to the next thing? Anyone? Okay, good. No question here. All right, let's go. Okay, let's look at this question we want to solve now. So now I know some people get scared with matrices. I know I used to also. In 2021, so I applied for an internship with Goldman Sachs. And then I think they gave a code signal. And code signal is like 4 questions, right? I think it was code signal, if I'm not wrong. Yeah. So code signal has 4 questions, 1, 2, 3, 4. Question 1 is usually, very manageable. You can just brute force your way and go. Question 2 to then question 3, right? Was it Goldman Sachs? I think it was Meta University. I don't remember, honestly. Or both. I don't know. Then, the question 3, I think was a matrix question, right? And I'm like, matrix 6, bro, that's so not friendly, right? And you can guess what happened. Okay. But matrices, graph matrices are like some of the coolest, right? It's so cool. I'll show you. It's so easy to write a code. So let's see. So assume we have, a matrix like this, right? And now, I showed you one way of representing it this way, right? So this is one way. There's also another way, right? This is like this and this have relationship, this and this have relationship. It's just for intuition. But let's look at this. Now, let's come here, right? Everybody fix your eyes here. It's going to be a bit tricky. Here's where we swerve, but let's go. The question I'm going to solve is simple, right? Actually, let me print a question. Yeah, I have a question. It's a bit tricky, but just bear with me. It's a bit tricky. It is really a bit tricky, but just bear with me. Okay. So we have something called, it's actually very popular algorithm actually. You have something called the Pacific Atlantic water flow. Pacific Atlantic water flow. Okay, so let's see what the question is saying. So, you have a graph like this, right? You don't even tell it's a graph, right? Like you have something like this, right? Then there's, there's water here, right? Now the blue water is what we call the Pacific. There's a blue water here. There's a Pacific water here. Ghana borders the Atlantic Ocean, right? I think so. Then there's the Atlantic here. Atlantic here. Please follow me carefully. There's the Atlantic here, right? So this is the Pacific blue. So this is Atlantic. Atlantic. Pacific. Let's use blue. Pacific. And then Pacific again, right? And then the next thing you want to do is that now inside this grid, right? Look at something here. We only have numbers inside our grid, and these are the numbers are going to be. So if I have 5 here, right, and I have 4, and I have 2 here, what this means is that water, right? Water can flow from the cell 5 through cell 4 to cell 2. In other words, if your neighboring cell is lower than you, you can flow, you can push water to it, right? So 5 can push water down 4, down to the Pacific Ocean, right? Does this make sense? But 2 cannot push water to 4, right? Because 4 is because to think of this as walls, right? Like water can overflow this wall into this, into that, right? But then it cannot go, the other direction. So that's basically what I want you to think about. Okay, so thinking about that, let me just fill these numbers randomly. I think that's fine, right? So does it make sense to everyone? Does this make sense to everyone? What the problem is? So I've not told the problem, but like, does this so far make sense? This setup, right? So here, if you look here carefully, right? So water can flow from cell 8 through 5 through 1 even to the Atlantic Ocean, right? But then water cannot flow from 7 to 8 to 9 to the Pacific. That's not possible, right? That's basically the problem. Now the problem they want us to solve right now is we want to find all cells, right? Find all cells from which, right? From which, so I think these are like lands or anything you want. I'm just calling them cells, from which water can flow from both to the Pacific and Atlantic Ocean. Both to the Pacific and Atlantic Ocean, right? So basically what they want us to solve is now, where's this thing, eraser, okay. So they want us, find a certain cell, right? That water can flow from both to the Pacific and Atlantic, right? So if I take, let's say, cell 5, also one thing I didn't add is, if they are equal, water can flow across, right? So if I take this cell, this 5 here, right? Water can flow from this 5 to this 4 to this 2. So from 5, I can go to the Pacific, right? Let me use a color to illustrate it. So from 5, we can go here, then come to the Pacific, right? And from that same 5, we can also go here and go to the, the Atlantic. So this cell should actually be selected, right? If I take this cell 3, right? This cell 3 too, the same thing can happen, right? Cell 3 can go into the Pacific straight, right? You can just go into the Pacific. Cell 3 can also go through 1 into the Atlantic, right? Now, does this problem make sense? Please take a few seconds to just think through it, right? And these are statements we have here. When you're done, you can just type into the chat, yeah, or me just be like, yep, sounds good. Before we go on, I'm going to show you another intuition to solve graph problems. It's a very useful thing. I want to show you reverse thinking, right? Like you think reverse. But look at this first, make it make sense to you before we proceed. When I think I'm putting the chat done or something. How we are thinking through. Are we done? Yeah, definitely need to go over that. Yep, good, done. Let's go. Okay, so this is a matrix, right? This one adjacency list. But if you look carefully, right, matrices are just, numbers, right? They're just numbered. So follow me carefully. So what we're going to do now is, right, let's move this guy up. Okay, let's move him up here, right? So what we're going to do now, follow me carefully. It's a very pretty algorithm. So if I have, please follow me carefully. I beg you. Okay, so when you look at this one, right, we're able to know, the concept of neighbors by saying key them values, right? So the values were its neighbors, right? But for a matrix, right, a matrix question like this, it's also relatively simple, right? That the neighbor of a cell is only those cells, right? They tell you, the water can flow 4 directional, right? North, south, east, and west, right? So if I take this cell here, right, the water can go up, right? Can go up, the water can go down, right? It can go left and it can go right, right? So this is how we go about it. So first of all, right, we're going to create something called the directions, directions. That's how I like to do mine. But another way you can also do it is, let's select this cell here, right? Let's select this cell here, right? This cell here. Now let's assume it's row and column, right? So this cell is row, comma, column, right? For a matrix, you can access, this box by choosing the row, right? When you choose the row, then you choose the corresponding column, right? Row and column, right? This row and column. To get its neighbors, right? 4 things. Its neighbors are in 4 directions. 1, 2, 3, 4, right? So this is how we do it. It's row plus 1, then you maintain the column. This is how you get the neighbors. Then row minus 1, you maintain the column. Then now you maintain the row, then you manipulate the column. This is just a pattern, right? That is how you get, the 4 directions. So if you look at it carefully, row plus 1 means come down, right? Come down to the next row, right? Then maintain the column. So the same column, but then you come down the row, right? So that's, this thing we have here. That's this one here. Now let's go to the next one. At row minus 1, then a column. So this is the row again, right? Minus 1 means come up, then maintain the column. So that is here, right? Then, similarly, column plus 1, maintain the row, and then here, right? So these are the 4 neighbors. These are the positions of the 4 neighbors, right? So that's how you get the 4 neighbors. So number 1, for matrix graphs, so you get the neighbors this way. So what I usually do is I just do this. I create a directions list like this, directions, a list of lists, maybe like 1, 0, 0, 1, minus 1, 0, 0, minus 1, right? Then I just use a for loop, right? I'd be like for the direction row in direction column in my directions, right? I know it's my weird thing. Now like neighboring row, neighboring column, it's equal to the current row plus direction row, comma. Let me just write the code cleanly for people to easily see that the neighboring row is going to be row plus the direction row in the neighboring column is going to be the column plus the direction column. So what I'm basically doing here is this. So, these things, right? This thing is like, the row plus 1, right? So that's like add 1 to the row, maintain the column, right? So the neighboring row, right, is going to be the row plus the direction row, right? So if it's this first one, it's going to be R plus 1 for the new row, right? The neighboring row, then the column is going to be maintained. But if you don't want, you can simply write these 4 things, right? Then the next thing I will do is that I'll then call the function. So let's say we are doing the function. Let's call it solve, right? And it takes the row number and the column number, right? So and I can then call solve on the neighboring row in the neighboring column. I'll come back. Don't worry. I'm just showing you how something like this can be done. Okay. So now let's go back to what we have here. I just wanted to see the parts of a graph question like this. Now let's continue. So this I can get the neighbors, right? Can use a for loop like I do. I can just write the 10 4 lines like this. Okay. Let's look at the next thing also. Wait, does this make sense? How what these things are? Like they're the neighbors, right? Just the neighbors, right? If this is row column, I can find the neighbors by just doing this. Add 1 to the row, maintain the column, separate 1 from the row, maintain the column, and so on and so forth, right? Okay, that's good. Then the next thing we do is that, so brute force, we can simply start here, right? We can simply start at, any cell. Then we can just use the condition, right? We can just use the condition, right? So this is what I'm talking about. So I'll check if, let's say we call this matrix. So if matrix, right? Look at something here. If matrix, right? Index row, index column, this is something we talked about 3 weeks ago when doing dynamic programming, how to, access elements inside a grid. We said first access the row, then access the column, right? If matrix row column, right? Now we are checking if water can flow, right? Can water flow from the cell R, C to the neighbors, right? So now we are taking it each neighbor at a time, right? So when can water flow? Water can flow if the value here is bigger than or equal to the neighbor, right? So if the value here is bigger than or equal to matrix, matrix of row plus 1 and column. So we're doing like for the first one, right? We're doing for this guy. We're doing for, this first guy, right? Then water can flow, right? Then water can flow. Water can flow, right? Then you do like the same if, you do this, then you do the same if for this, then the same if for that. Does this make sense? Then water can flow. Does this make sense? I just want you to just let this sink in. Does this make sense? Does this code I've written here make sense? I want to check if this thing here makes sense. Okay, now let's proceed. Now, because we already know this guy, I want to erase this guy here, right? And then I want to start writing like pseudocode, at least some good code, right? So let's write the function. So let's call the function can flow, right? Can flow. And can flow is simply R, C. And can flow is simply a function that tells us if water can flow from, from this cell, right, to an ocean. So let's say to the edge. If water can flow from this cell to, let's say, any edge. For now, just think of any edge, right? So can flow returns true if water can flow from this cell to any of these guys, to any of all the 4 areas, right? So that's so now assume the function works, right? Assume the function works. So as we are doing now let's look at something here. So the general algorithm, let me enlarge this so you can see here. So general algorithm is I'll take every cell here. Please follow me. This is just a brute force solution. I just want to get a brute force, then we can write it down. So the brute force solution is I'll select each cell, right? Then I will simply call, can flow. I'll call can flow, right, on that cell. That, hey, can water flow from you to any of these, any of these areas, right? And how do I know? When I call the function here, right, I'll call it on each of its 4 neighbors, right? Each of its 4 neighbors, right? And if each of its 4 neighbors goes out of bounds, right, out of bounds, that means that I've been able to locate it. Does this make sense? That I'll call can flow, right, on any cell. So if I choose cell 5, this cell here, then I'll call can flow 4 times, right? 4 times. In other words, or first I'll get the 4 neighbors of this cell, right? If I get the 4 neighbors of this cell, and any of its neighbors, right, is out of bounds, then I know it can flow into the ocean, right? Doesn't mean I should repeat it. Doesn't mean I should repeat it. I know it's a bit, but once you get it, I chose a very difficult question, but I think if you get this question, you can solve many matrix related ones. But does this make sense? Right? Let me write it out. I think that will make more sense. So when can I know water can flow to it? Number 1, I get the neighbors, right? So again, and let's say the neighbors are now NR, NC, right? Now, if the neighbors, right, if the neighboring row is out of bounds, what do I mean by out of bounds, right? Let's assume it's less than 0, right? That means that we have got here, right? If it's less than 0, so this is the neighboring row. If it's less than 0, that means I'm here, right? And this is actually water because this is row 0, right? So if it's less than 0, like -1, that means I'm here. Does this make sense? Like if the neighboring row, so like if I take this cell here, right? If I take this cell here, if its neighboring row is up here, that means it can go, right? Water can flow from here to here, right? In the same way, if I take the neighboring row, right, and it's greater than, the number of rows, I usually call it, let's just call it n rows, right, -1, right? So this is the last row. This is the last row number, right? If it's greater than 8, that means here. That means you can equally get here, right? So if I take this cell here, and what do you call it? And this neighboring row is like this value here, that means you can get there, right? Then the same way, you do the same thing for the column, right? If the neighboring column, right, is also less than 0, right? So this is like the first column. This is a first column, right? This is a first column. So if it's here, right? If this is here, this is the column, right? The columns are the vertical ones. So if it's here, that means the same way, and then I can do the same thing for this. Please, does this make sense? The number of columns -1. I'm just showing something out of bounds. Like this is what we call the out of bounds thing, right? Before you make a recursive call each time, you have to check this out of bounds thing, right? Else you're going to get, index out of bounds error. But please, does this make sense? For this question, we know you can get to an ocean if you find your neighboring column and they are like something like this. Does this make sense? I know it's a bit tricky, but take your time. Take like some 10 seconds to just look at this. That if I find your neighboring row and your neighboring column, right, and they are here, that means we can actually get to the ocean. Okay. All right. Okay. It makes sense to some people. The rest of you, if you have a question, can be like, please wait. Can you go over this again or something like that? Then we go over it again. You have like 10 minutes to be done. So ask any questions if you have, right? So if I find a neighboring row and a neighboring column and, they're out of bounds, that means you can indeed get to the ocean, right? So with that in mind, right, what I can simply do is I can just select a certain cell, right? I can just select any random cell. I mean, for now, I won't select every single cell. So I'll select this first cell. This is using a for loop, right? Select this first cell, right? Find its neighboring rows and its neighboring columns, right? Its neighboring row and its neighboring column, right? So then I can make a recursive call on them, right? So let's just write the code here. So our base case, right? Our base case is if, right? If these things, right? If these things, right? So let's just call them conditions, right? Conditions. So if the row is out of bounds, so I can simply do, I'm not going to write that code in Python very clean. It's simply if not R in range number of rows, or not C in range, number of columns, return true. That means I can get to the ocean. Look at what I just wrote here. You know, range number of rows simply means from 0, right? Range means from 0 to this value minus 1, right? So that means that from 0 to the value minus 1. So if it's out of bounds, that's if not, that means, you know, you can get to the thing, right? And the same thing for the columns, right? So if that row in that column, that means that they're out of bounds. So you are supposed to return true, right? For whichever, you know, cell triggered you. So if it was this cell that triggered you and you got here, return true to it. Be like, you can get there, right? Does that make sense? Okay. Then let's go to the recursive case. Let's go to the recursive case. We're almost done. We're almost done. We're almost done. We're almost done. You can go to the recursive. Then our recursive case is going to be now go through all the neighbors, and we wrote that code initially, right? In, you know, directions, right? I think you can do it 4 times, but I just, you know, did it this way. Then I can simply, you know, find the neighboring row, find the neighboring column, right? Now we know how to find those things, right? Then I can simply check if can flow, right? If can flow, right? Any of its neighbors, neighboring row, neighboring column, right? I can return true for this guy, right? Can return true. Does this code make sense, right? I find its neighbors like we did NR and NC. Then I call the function on it. If any of them returns true, that is, if you're able to float to any of them, you return true, right? But then when do you return false is the question, right? When do you return false? Now, before you trigger this recursive call, you then do the check with it. I've deleted it. Oops, sorry, I've deleted. Let's throw that one in here. So we can simply check, right? When you want to trigger the recursive call, right? Can flow when you trigger the recursive call. If you trigger a recursive call, if water can flow from here, you know, to that next cell, right? So you simply check if matrix, there's just a slight change. I'll do later, but don't think about that now. If matrix of, you know, row and column, right, is greater than or equal to matrix of neighboring row, neighboring column, right? That is when you should trigger, you know, the recursive call. Then check can flow, neighboring row, neighboring column. Yeah, I know it's a bit tricky, but what we are simply doing here is we really want to, you know, check if we can flow from you if, you know, this value of the current cell is greater than the neighbor, right? Somebody is thinking, what if this guy is out of bounds? Yeah, that's true. That's a case you can put here, but don't think about that for now, right? So we're simply checking that, okay, so if I'm at 5 here, right, I want to check if I can flow to 4, right? But I can only flow to 4 if 5 is bigger than 4, right? So if 5 is indeed bigger than 4, check if you can flow from 4, right? That's what the recursive case is doing, right? So R comma C is 5, right? This is 5. You're like, okay, go through 5's neighbors, choose one of the neighbors, 4. Check if you can flow, you know, from 4 to the ocean. I'm like, but first, before I check if I can flow from 4 to the ocean, before I check if I can flow from 4 to the ocean, first check if you can even flow from 5 to 4. That is what this case is doing here, right? So that is what you're doing. You're like, if you can flow from 4, right, to the ocean, then you return true, right? That's simply what this thing is doing here. Does this make sense? I know it's a bit mentally tasking, but does it make sense at least what we've written here, right? Like we select this guy here. Can we flow from you? Then we check your neighbors. Can we flow from your neighbors to it? But there's a condition that to flow from me to my neighbor, I have to be bigger than my neighbor, right? Or bigger or equal to. That is what we have here, and that is it. Does this make sense? Does this make sense? Does this make sense? And this is the brute force approach. I'm not coming to explain the optimized one, which is very intuitive. It's very cleaner than this. But I just want you to understand the brute force algorithm. Because you come through some questions where it's important to, you know, use this. Where you start from some place, you know, every cell and then it starts. But before you go on to the cleaner version, does this at least make sense? That you take, you know, a node, you know, check some condition, whether you should go to the next cell or not. That condition is very important. You could do some questions. The condition is, you know, check if the next cell is 1. I'll try this question called rotten oranges, and that's a different version, right? Okay, now let's go to the cleaner version. So if somebody looks at this, the person will be like,
yeah, I have a question.
Yeah, what's your question? Yeah, let's go ahead.
Yeah, about the solution. Like I was thinking like, so if like let's say we are moving from, can you go up a little bit? I want to use the matrix here. If we are moving from 5 to, let's say we're moving from the 5 that you circle to the 4, right? When we do the recursive call from the 4, won't it also like check the neighboring ones, the neighboring cells, and like per the question, I'm supposed to check like from left to right, up to down, not from left to right to down or something like that.
Oh, so you can go forward, you can go in 4 ways, so you can go all 4 ways, right? So from 5, we go to 4, right? But can somebody see that if you go to 5, from 5, you go to 4, 5 is also a neighbor of 4, right? So if you are checking false neighbors too, 5 is also going to be in. And it can be stuck in a recursion. We call it something hell. I've been forgotten, right? So that's why the vested,
something like that.
Like you don't want a cycle, right? So you see that cycle thing we discussed is the same thing. If you check out 5, you put 5 in your vested sets, right? Then you go to process false neighbors and you see 5 in there, you don't check 5. Else from 5 you go to 4, right? False neighbors, 5 is also in, you come to 5 again. 5's neighbors, 4 is in, right? You're going to be stuck in a recursion hell, right? So you put 5 in a vested set, you come to 4. So here, false neighbors, you only process 3, 0, and 9, right? Then let's say we come to 0. Then 0 to be processed 1 and here, right? Then we get, and 0 was able to lead us to the ocean, right? So 0 is going to, this guy is going to return true to 0, 0 return true to 4, 4 return true to 5, right? Then you can be like, okay, we could get to it from 5. Does that make sense? So that's what is going to happen there, right? I thought I'll show you a code. I'll show you an implementation of it. Okay. But now let's see something here. Let's look at the time complexity of this algorithm we have here. So can flow simply means, can we flow to the ocean, from this cell RC? That means that we want to check if we can flow from every single cell. Please follow me carefully. This is so important. If everything I've discussed at first didn't make sense, just follow me at this point. So can flow is like, can we flow, to the ocean from every cell? So we have to start from every cell. Every cell has to be a starting point, right? So I start from this cell. Can I flow from you? Right. So if I start from this cell, I have to explore its neighbors. I have to explore. Can I get to the ocean from you? So I'll explore here. This will return true. But then you also check this guy. You also check this. I also check up here. So that is true. Then it starts from 8, right? But you know that when you come to the 2 here, 2 does not end. 2 can go here, 2 can go here, 2 can go here, right? If you start at, so there's going to be a lot of work, right? Except from everything, it's going to be a lot of work. Just take time and check it. If you start at 8 will come here, right? Then you go here to go here to go here to go here. That's like a lot of work. It's going to be a lot of work. So instead, if you look carefully, there's something smarter we could do. And it's actually reverse thinking. Just look at it carefully. Instead of starting from a cell and trying to go out, let's start from out and try to come in, right? Follow me carefully. The naive solution we did, the beautiful solution we did was start at, any cell, right? Then use the condition they gave you, right? Use the condition they gave you. What was the condition again? Use this condition, right? Use this condition we have here and then flow out, right? Start at a cell and try to see if you can flow out to the ocean. Now, why don't we start from the ocean and try to flow out, right? That's a very smarter solution, right? So let's start from the ocean. So this we can be like, every cell on the edge, right? Every cell on the edge can actually get to, the ocean, right? Can get to a certain ocean. If I start like at this first row, they can all get to this part. They can all get to the Pacific, right? They cannot get here. If I take this whole guys here, they can also all get to the Pacific, right? If I take this one, they can also all get to the Atlantic, right? You can all get there. The same thing for down here. So far, that's what I've said just makes sense. Does this make sense? Right? That all the, the edges ones can get to some ocean, right? They cannot get to the ocean. Even if I take this, I can get to both oceans, but don't think about that for now. All these ones can get here. All these ones can get here. All these ones you can get here, right? I hope everyone agrees with that. Can everyone agree with that? We're doing reverse thinking. Instead of going from here to here, we now come to start from here to come in. And you see how to just make things cleaner. Okay, can we proceed? Can we proceed? I want at least 2 yeses before we can proceed. Okay, we have a yeah from Jude. Anyone else? Good. So how are we going to do that? We're now going to flip the condition. Now look at something. We said that we can flow, let's use black. We can flow from 5, right? We can flow from 5 to 4, right? If 5 is bigger than or equal to 4, right? Then by reverse, we can flow from 4. Let's use something else. Let's make this 12. Then by reverse, we can flow from 3 to 12 if 3 is also less than or equal to 12. Does that make sense? So we are only going to trigger the recursive calls, right, from the, the cells on the edges. And then we're going to just flip that condition, right? At first it was like, hey, from inside to out, you need to, be bigger than or equal to. But now from out to inside, it needs to be less than or equal to, right? So here, so we start from 2. 2 is less than or equal to 4, right? That means it's possible, right? They were like, okay, 4, 2 is less than or equal to 5. That means it's possible, right? So that means that we can get to the ocean from cell 2, from cell 4, from cell 5, right? We can get to, this Pacific Ocean from there, right? But now let's see if we can get to the Pacific Ocean from, cell 4, right? Just using, this path, right? We're like, no, 5 is not smaller than 4 or equal to 4. Therefore, from 5, we can go here, right? So for this path, we can simply be like, this one's work, right? And then we stop there, right? In the same way, we start from here, right? 3 is less than, so we start from here. So 3 is possible. Then we come to 4, 2, it's possible, right? And then we're like, okay, then we can get here. Does this make sense? Does this make sense, someone? Does this make sense? Like, this is the main takeaway I want to get from it. That sometimes, instead of starting from inside out, which will work, but it's a lot of brute force, right? It's a lot of work. Start from outside and just come inside. This guy's going to make a solution clean. Now, let's see how he makes a solution clean. The solution is clean in the sense that every cell on which we call our function is going to be in the result, right? Because we're going to only call the function, right? We're only going to call the function if you are, you are bigger than, the current row or column, right? The current cell. So if I'm a 2 here, right, I'm going to check, hey, 4, are you bigger than 2? Then I'll call the function on you so I can accumulate you. 5, are you bigger than 4? Yes, then I'll accumulate you, and it's just simple. Now let me show you the code. What we'll learn next week, we'll go about this again, but I'll add it to this week's practice problems for you to play with it yourself, then we go through it. But I just want you to know that sometimes you don't have to start from inside out, which is very, possible. Then you just start from, outside, and then you come inside, right? This question is important in the sense that, it teaches you how to write one function and use it twice. So you see in the solution, we're going to write the function once, but so if you look at something, the Pacific can only be touched by, for the Pacific, we start the function calls only on these cells, right? These ones here, only these ones here. So you write one function, then you start calling that function from these cells. Then that same function, you reuse it, but now you start calling the function from these cells. So the results you got from the first one, from the Pacific ones, you intersect it with the results you got from the Atlantic one, right? That means that they can get to both the Pacific and the Atlantic, and that is your output. Very cool stuff, I know. Let me show you the solution. Let me share my screen and show you the solution. Then we actually done. I know, mentally draining, I know. We are almost there, almost done, actually. Let me open, I want to open the question and then show you the solution. I wrote, actually saw this question like very recently. So good stuff. Also, I was practicing with a friend and they chose this question like last week, and I'm like, okay, cool stuff. Okay, can we all see this? This is a question. Yeah. Whoa, I use the same Pacific and Atlantic. Exciting. Okay, and this is the implementation I wrote. So it's the same question we discussed, right? So let's look at something here. I call it flow, can flow, right? So this code I have here, it's simply, finding the cells through which, water can flow from to the Pacific. But I said think reverse. Think of it as the cell through which water can flow from the Pacific to it, right? So I use just one function called flow, right? This is the flow function, right? So this is the thing I said, right? I create the directions thing, right? I mean, you can also call it like 4 times, anyhow you want to, but I think this is cleaner. So this is the current row and column. So assume like is this one, right? Then you get the neighboring row and the neighboring column. Then you check, these are the conditions, right? These are like the conditions which prevent you from flowing. What are the conditions? 1, if it is out of bounds, or 2, right? Here's the second one. Or 2, if the neighboring one, right, is smaller than it, right? Like I'm coming inside, so 2 should be bigger than 1, right? 2 should be bigger than 1. It's like just a reverse thinking thing, right? So then you do it. If not, you just call flow on the neighboring cell, right? And like the code is just so clean and it's so better, right? So it's just the same function. I just call it like 4 times. I mean, twice for the Pacific. This first one you can see here, it's me calling it from here, like from here, right? Like actually it's from here, right? Call from here. That is like I maintain the column 0, right? This column 0, but then different rows, right? I check all the cells through which you can flow water from the Pacific. This body is the Pacific. Flow water from here to these ones, right? Then I get them, then I accumulate it into my Pacific sets. Then I do the same thing, for here, this one, that is like maintain the row, row is still 0, maintain the 0th row, but change the column. So column this, column this, column this. Then I get that set. So that's going to be stored in the Pacific. As you can see here, I accumulate it here. Then I do the same for the Atlantic, then after I just find the intersection, I just return it. Very cool stuff, right? Then let's submit again. I like submitting multiple times. Yeah. When was this? Let me see the code I wrote for this guy. I have no idea. Okay. But yeah, very, very cool stuff. So yeah, that's it for today. Call in tomorrow. I know the matrix one is a bit tasking, but it's actually not. Just, the neighbors, now instead of taking the neighbors from some dictionary, take the neighbors by just using this manipulation. +1 - 1 +1 - 1. Then you check some keys here. You always have to check is inbound, right? Because if this is out of bounds, right? If neighboring is out of bounds, what is going to happen is that if you do this, it's going to give you an error, right? It's going to give you an error because it's going to be like it's going to be like something outside here, right? So that's something. I'll actually give you a couple of problems you can try this week, and it's very helpful. Wait, am I sharing my screen? Wait, am I sharing my screen? Wait, am I sharing my screen?
Yes.
I am. I thought I was not. Okay, good stuff. Okay, so if you didn't watch last week's recording, please do well to watch it. Please do well to watch last week's recording. I think it's easier to understand this week's if you watched last week's. So watch last week's recording if you didn't, and then watch this week's. And I think it should be good to upload this thing too, so you can rewatch it anytime. And all next week we do more problems, and we will probably do a question on tries, I think. And yeah, we should be good. Yeah, so that's it for today. Thanks. If you have any questions, ask in the channel and we will get back to you. I hope people are practicing. Please make time and practice. Tell people to practice with. Let us know if you're in a group. Please make time, practice with them. It really helps. It really helps. It's really helps. Practice a lot, and yeah. All right. Thanks everyone. Yeah. Any questions? Nothing. If not, bye.